The cosmic dance of atoms, from nothing to everything. Our entire universe, from the device you're watching this on to the air you're breathing, from the farthest galaxies to your own body, is constructed entirely of atoms. These infinitesimal building blocks form the foundation of everything we know. But have you ever stopped to wonder, where did atoms come from? How did they emerge from nothingness? And could our entire universe, vast as it seems, be nothing more than a single atom in a much larger reality? Picture an atom in your mind, a tiny nucleus surrounded by electrons whirling around it at incredible speeds. This simple mental image leads us to an intriguing question that plagued physicists for decades. How do these electrons maintain their perpetual motion without gradually losing energy and spiraling into the nucleus? This seemingly straightforward question launched one of the greatest scientific revolutions in human history, the development of quantum mechanics. It forced us to completely reimagine the fundamental nature of reality itself. The quantum revolution, reimagining the atom. In the early 20th century, scientists were intensely focused on deciphering the mysterious structure of atoms. They had established that atoms contain a nucleus with positive charge and significant mass, surrounded by much smaller, negatively charged electrons. With this foundation, they set out to build a comprehensive model of atomic structure. The first intuitive approach was to envision atoms as miniature solar systems, dense nuclei like the Sun with orbiting electrons like planets. But this elegant model immediately ran into two critical problems. First, according to classical physics, charged particles in motion should constantly emit electromagnetic radiation. Since electrons are charged and orbit continuously, they should rapidly lose energy by emitting radiation, causing them to spiral inward and collide with the nucleus within a fraction of a second. Yet atoms are remarkably stable, existing for billions of years without collapsing. Second, when scientists observed atoms emitting light, they found distinct, specific frequencies rather than the continuous spectrum predicted by the solar system model. Something profound was happening that classical physics couldn't explain. Enter Niels Bohr, the brilliant Danish physicist who would forever change our understanding of atomic structure. In 1913, Bohr proposed a revolutionary idea: electrons don't orbit randomly but are confined to specific, quantized distances from the nucleus. More importantly, Bohr suggested there exists a minimum distance that electrons must maintain from the nucleus. They simply cannot get any closer. Bohr's insights weren't mere speculation, they built upon the groundbreaking work of Max Planck, who had introduced the concept of energy quantization a decade earlier. Planck had discovered that objects absorb and emit radiation only in discrete packets or quanta of energy, never in arbitrary amounts. These packets were defined by a new fundamental constant of nature, Planck's constant. Building on this quantum foundation, Bohr proposed that an electron's smallest possible orbit must possess angular momentum exactly equal to 1 Planck constant. Larger orbits could have values of twice, 3 times, or other integer multiples of this constant, but never fractional values like 1.3 or 2.6. This explained why electrons couldn't gradually spiral inward, they could only jump from one allowed orbit to another, never existing in between. Bohr's model was revolutionary, but understanding why electrons behave this way required the full development of quantum mechanics. The true nature of electrons proved even stranger than Bohr imagined. Waves of probability, the true nature of electrons. Our common-sense view of electrons as tiny particles orbiting the nucleus, like planets around a star, turns out to be fundamentally incorrect. Electrons, like all matter, exhibit a mysterious dual nature. They behave as both particles and waves simultaneously. Rather than thinking of an electron as a miniature planet orbiting a nucleus, it's more accurate to envision it as a wave enveloping the nucleus. When constrained within a limited space, like an atom, these waves must follow special rules. They cannot have arbitrary wavelengths but must form standing wave patterns that precisely fit the available space. This is similar to how a guitar string works. When you fix both ends of a string, only certain vibration patterns produce clear notes. Similarly, the electron wave surrounding a nucleus must match the available space, with the smallest possible orbit determined by the first standing wave pattern. As quantum mechanics advanced, physicists refined this model, discovering that electrons don't follow defined paths at all. Instead, they exist as probability clouds, regions around the nucleus where they might be found if measured. The densest parts of this cloud represent locations where the electron is most likely to be detected, while sparser regions indicate lower probability. This probabilistic nature isn't due to limitations in our measuring equipment. It's a fundamental property of reality at the quantum scale. Electrons don't have definite positions until they're observed, they exist in multiple potential states simultaneously. This strange behavior, called quantum superposition, defies our everyday intuition but has been confirmed by countless experiments. Another way to understand why electrons don't crash into the nucleus involves energy considerations. An electron orbiting a nucleus experiences an electromagnetic attraction pulling it toward the nucleus. Simultaneously, the electron possesses kinetic energy that pushes it outward. For a stable atom, these forces balance. The total energy of an orbiting electron, combining its kinetic and potential energies, is negative, meaning energy must be added to remove the electron from the atom. This parallels how energy must be added to remove a planet from a solar system. The reason electrons maintain stable orbits ultimately stems from quantum mechanical principles. An electron cannot approach the nucleus beyond a certain limit because quantum constraints prevent it from occupying a smaller space. The atom remains stable because the system's total energy is negative, binding its components together. These quantum principles don't just explain atomic stability, they underpin the very existence of matter as we know it. Without quantum mechanics, atoms would collapse, chemistry would be impossible, and life could not exist. The cosmic birth of atoms, from the Big Bang to the first elements. Everything surrounding us, from the device you're using to your own body, consists of an unfathomable number of atoms. The observable universe contains more than 10 to the power of 80 atoms, a number so vast it defies comprehension. Each atom contains electrons, protons, and neutrons, which themselves contain even smaller particles called quarks. Where did all these particles come from? Their origins trace back to a monumental cosmic event, the Big Bang. The Big Bang theory serves as our guide to understanding the universe's beginning, suggesting that the cosmos began with an incredible concentration of energy that expanded to form everything we know. But understanding how atoms formed requires us to examine the early universe in greater detail. The exact moment of the universe's beginning remains mysterious. The standard model of cosmology suggests a singularity, a point of infinite density where all matter and energy were compressed into an infinitesimal space. However, many physicists question whether this mathematical singularity actually existed in physical reality. Our scientific understanding can take us remarkably close to the beginning, back to approximately 1 Planck time, about 10 to the power of -43 seconds, after the Big Bang. Before this infinitesimal moment, our current physical theories break down, and the story of the primordial universe eludes us. To truly understand these earliest moments would require a quantum theory of gravity, a framework that unifies the physics of very massive objects, governed by general relativity, with the physics of the infinitesimally small, governed by quantum mechanics. This period, known as the Planck epoch, occurred at an unimaginably small scale. During this epoch, all 4 fundamental forces, electromagnetism, the weak force, the strong force, and gravity, may have been unified into a single, grand force. The universe was a seething plasma of pure energy, far too hot for particles to form. Rather than attempting to describe the enigmatic singularity at t=0, let's begin our journey at a point where our theories offer more confidence. Our theoretical exploration starts with the epoch of inflation, occurring from approximately 10 to the power of -36 to 10 to the power of -33 seconds after the Big Bang. During inflation, the universe underwent extraordinary expansion at a rate faster than the speed of light. This didn't violate Einstein's cosmic speed limit because it wasn't matter moving through space, it was space itself expanding. In this brief moment, the universe grew from a subatomic scale to roughly the size of a grapefruit. While inflation provides fascinating insights, our most solid understanding begins in the period that followed. Here, the Big Bang wasn't a point in space and time but an epoch when the extremely hot, dense universe expanded rapidly. As we move forward in cosmic time, the universe continued cooling and expanding. At around 10 to the power of -12 seconds, energy levels had dropped enough that they match what we can recreate in current particle accelerators, giving us more confidence in our models from this point forward. Before this time, during the period from approximately 10 to the power of -33 to 10 to the power of -12 seconds, the fundamental forces of nature were still partially unified. Gravity had separated, but the strong force and the combined electromagnetic and weak forces, called the electroweak force, remained unified. The birth of elementary particles, building blocks of atoms. How did the first massless elementary particles emerge? Multiple theories exist. One possibility suggests they were born directly from the energy of the Big Bang. Another hypothesis proposes they formed when an inflation field transformed into the elementary particles populating our universe today. This cosmic genesis occurred around 10 to the power of -11 seconds after the Big Bang, when the temperature dropped to approximately 10 to the power of 15 Kelvin. At this pivotal moment, the electromagnetic force separated from the weak force in a process called electroweak symmetry breaking. Simultaneously, the Higgs field acquired a non-zero potential, granting mass to elementary particles as described by the Standard Model of particle physics. With these fundamental components in place, the universe's temperature hovered around 1 quadrillion Kelvin. As the cosmos continued expanding and cooling, the scorching temperatures initially prevented quarks from combining into composite particles like protons and neutrons. However, as the temperature gradually fell to approximately 1 trillion Kelvin around 10 to the power of -5 seconds, a remarkable transformation occurred. The quark plasma metamorphosed into a hadron gas featuring protons, neutrons, and specific mesons. These mesons subsequently transformed, creating photons and electrons. With each temperature decrease, a symphony of particle-antiparticle annihilation ensued, generating pairs like neutrinos and photons. A subtle asymmetry in this process allowed slightly more particles than antiparticles to survive, providing a cosmic loophole that permitted certain quarks and electrons to endure. This asymmetry, though small, proved crucial for the universe's future, as it provided the necessary ingredients for atoms to eventually form. This intricate choreography of particles and forces set the stage for the cosmic narrative to evolve. The annihilation process concluded with the lepton epoch around the 1-second mark, when temperatures had dropped to about 5 billion Kelvin. During this time, leptons completed their annihilation with antileptons, leaving a universe dominated by photons and neutrinos. Because of the tiny matter-antimatter asymmetry, a small remnant of protons, neutrons, and electrons survived, becoming the essential building blocks for atoms. Around 3 minutes after the Big Bang, the era of Big Bang nucleosynthesis, BBN, began. During BBN, protons and neutrons could finally combine to form atomic nuclei. Free neutrons are inherently unstable, transforming into protons through beta decay in about 10.5 minutes. While temperatures remained high, the conversion between protons and neutrons maintained balance. But as the universe cooled, neutron decay became more prevalent. Neutrons that didn't decay tried to combine with protons to form larger nuclei. This process resulted in a universe composed of approximately 75% hydrogen nuclei, single protons, and 25% helium-4 nuclei, with small amounts of deuterium, helium-3, and trace amounts of lithium-7. However, these weren't yet complete atoms. For the next 380,000 years, the universe remained too hot for electrons to stay bound to nuclei. The cosmic landscape consisted predominantly of ionized nuclei without stable electron companions. The first atoms emerge, recombination, and the cosmic microwave background. The formation of stable, neutral atoms required electrons to bond permanently with positively charged nuclei. However, the early universe remained too hot for this union to last. Whenever an electron joined a nucleus, its high energy would quickly tear them apart again. This created a cosmic fog where photons, light particles, constantly scattered off free electrons, making the universe opaque. Like light struggling to penetrate dense fog, photons could only travel short distances before being deflected, preventing light from traveling freely through space. This photon epoch persisted until the universe cooled to approximately 3000 Kelvin, about 380,000 years after the Big Bang. At this crucial temperature threshold, electrons finally had low enough energy to form stable bonds with nuclei through the electromagnetic force. This momentous process, called recombination, marked the birth of the first neutral atoms. Primarily hydrogen with some helium and traces of lithium, these atoms were the simplest forms possible, a far cry from the complex elements that would later form stars, planets, and eventually life. As electrons combined with nuclei, photons were suddenly liberated from their constant scattering interactions. Like fog lifting to reveal a clear sky, light could now travel freely across the expanding universe. These ancient photons continue their journey today, forming what we detect as the cosmic microwave background, CMB, radiation. The CMB represents the earliest light we can observe, a snapshot of the universe when the first atoms formed. When we detect this radiation coming from all directions, we're seeing the moment when the cosmos transitioned from an opaque plasma to a transparent sea of neutral atoms. This ancient light carries crucial information about the infant universe and the earliest stages of atomic formation. Scientists study tiny temperature fluctuations in the CMB to understand the density variations that eventually led to galaxies, stars, and all cosmic structures. The birth of the first atoms marked a pivotal transition in cosmic history. The universe had evolved from a seething plasma of elementary particles to a vast expanse of simple atoms that would, over billions of years, undergo further transformations through the influence of gravity and nuclear fusion in stars. The mystery of atomic interaction: do atoms ever truly touch? As we explore the fundamental nature of atoms, an intriguing question emerges: do atoms ever truly touch each other? This question probes the essence of what we mean by touch and interaction at the atomic level. Our conventional understanding of interaction stems from everyday experiences. When you push two magnets toward each other, you feel them either attract or repel. When two charged balloons come near each other, their charged surfaces interact. These macroscopic interactions, governed by magnetic and electrostatic forces, represent our intuitive understanding of objects affecting each other. But the microscopic world operates by different rules. At this scale, atoms and molecules engage in perpetual motion, colliding, twisting, and spinning in a chaotic symphony. When we examine atomic structure, we find no distinct boundary or solid surface. The nucleus contains clustered protons and neutrons, while electrons exist in probability clouds indicating where they might be found. Quantum mechanics allows us to calculate these probabilities, revealing that electron clouds technically extend infinitely far from the nucleus, though with rapidly diminishing likelihood farther out. In most practical scenarios, electrons remain relatively close to their nucleus. Since atoms lack solid surfaces, they don't touch in the conventional sense of surfaces meeting. However, touch also implies close proximity with meaningful interaction, and in this sense, atoms certainly do interact with one another. Atoms interact primarily through the electromagnetic force arising from the electric charges of their electrons and protons. Though this force has infinite range, it becomes significant only when atoms come sufficiently close. When two atoms approach each other, their electron clouds begin to overlap and interact. Sometimes atoms repel each other due to electromagnetic forces between their electrons. When this happens, we perceive what we call touch in everyday experience, though no solid surfaces actually make contact. Consider a cup sitting on a table. At the atomic level, the electrons in the cup's outer edge repel the electrons in the table's surface. Despite the microscopic gap between the electron clouds, the atoms are close enough to substantially influence each other, preventing the cup from falling through the table as electromagnetic forces counteract gravity. Atoms can interact in various ways beyond simple repulsion. When they approach each other, they experience the van der Waals force, a component of the electromagnetic force. Surprisingly, this force can create bonds between atoms, forming molecules where atoms are essentially in contact with each other in the only meaningful way possible at the atomic level. Even atomic nuclei can potentially touch, though this requires overcoming the strong electromagnetic repulsion between positively charged protons. Quantum mechanics makes this possible through quantum tunneling. If two atoms are brought close together and held for sufficient time, there's a small probability their nuclei can merge. This process, called nuclear fusion, occurs when two separate atoms combine into a single larger atom. When the atoms involved are lighter than iron, fusion releases energy, the fundamental process powering stars, including our Sun. The uniqueness of atoms. Are any two atoms truly identical? Are any two atoms of the same element truly identical? The answer reveals surprising complexity in what seems like a simple question. First, electrons in an atom can exist in different states. Two atoms of the same element may differ if their electrons occupy different energy levels. For example, one copper atom might have an excited electron while another has all electrons in the ground state. The excited copper atom will emit light when its electron returns to the ground state, while the ground state atom will not. How an atom forms chemical bonds depends on its electron states, so two atoms of the same element might react differently. Chemists understand this well. To accurately predict reactions, they must specify the ionization and excitation states of atoms involved. Beyond electron states, atoms' behavior is influenced by their movement and rotation. Atoms moving at different speeds form chemical bonds differently. Slowly moving atoms, like those in solids, have sufficient time to establish stable bonds. Conversely, rapidly moving atoms in liquids form less stable connections. A slow-moving tin atom behaves differently from a fast-moving one. Even if two atoms of the same element have identical electron states and move at the same speed, they still might not be indistinguishable. Like electrons, the neutrons and protons within the nucleus can exist in various excited states. The nucleus itself can rotate and vibrate at different rates. Two gold atoms might have nuclei in different excited states, causing them to behave differently in nuclear reactions. Beyond electrons, the nuclei of atoms introduce further complexity. The nucleus contains tightly bound neutrons and protons, and atoms of the same element can have different numbers of neutrons while remaining the same atomic species. These variants, called isotopes, behave identically in chemical reactions but differently in nuclear processes. Isotopes significantly impact nuclear reactions, particularly radioactive decay. Various isotopes decay at different rates and emit different types of radiation. In carbon dating, distinguishing between carbon-12 and carbon-14 is essential. Counting total carbon atoms wouldn't determine a sample's age. Despite these differences, it's important to note that atoms don't have individual identities beyond their physical states. If two carbon atoms have identical molecular, atomic, electronic, and nuclear states, they are truly indistinguishable, regardless of their history. The color of atoms, perception versus reality. When you view a computer screen displaying various colors, you might wonder, do the individual atoms making up the screen have colors too? If so, is it the nucleus or the electrons that possess color? This question leads us to explore the fascinating nature of color itself. Colors as we perceive them are created by the human brain. They don't exist as properties of objects independent of our perception. To understand color, we must first grasp the nature of light. Light consists of particles called photons that exhibit wave-particle duality. They behave as particles when observed and as electromagnetic waves otherwise. These waves have specific frequencies, classified into various wavelength ranges from radio waves, as large as Earth, to gamma rays, smaller than atoms. The human eye detects only a tiny fraction of this spectrum, the visible light range. Why can we see only this particular region? The answer lies in evolutionary biology. The first eyes evolved in aquatic environments, and visible light happens to pass relatively transparently through water, while infrared and ultraviolet light are partially absorbed. If early organisms had evolved in different environments, Perhaps sulfur lakes on a planet orbiting a neutron star, their eyes might have adapted to detect entirely different wavelengths, such as X-rays. Light originates in various ways, but ultimately all light results from changes in electron energy states. In the Sun's core, hydrogen nuclei undergo nuclear fusion due to immense pressure, transforming into helium and emitting gamma radiation. This radiation bounces around within the Sun, losing energy through collisions over thousands of years before emerging as visible and ultraviolet light that reaches Earth. When light encounters materials, it interacts in two primary ways: absorption and reflection. Different materials absorb and reflect different wavelengths based on their atomic and molecular structure. A blue fabric appears blue because it reflects blue wavelengths while absorbing other colors. Black objects absorb most wavelengths, heating up in sunlight, while white objects reflect most wavelengths, remaining cooler. These interactions depend on bulk properties, how molecules are arranged and spaced. Even materials with identical molecular composition, like snow and ice, can appear different. Snow is white, ice is transparent, because their molecular arrangements differ. Can individual atoms have colors? In terms of bulk reflection, no, light wavelengths are much larger than single atoms, making it impossible to discern colors at the atomic scale. However, atoms do interact with light in specific ways. When heated, atoms release photons with wavelengths forming a predictable spectrum regardless of the element involved. This thermal radiation doesn't reveal distinctive colors for individual atoms, it requires collections of particles. More revealing is gas discharge, when electricity passes through atoms, exciting them to emit photons. Each element produces a unique emission spectrum. Hydrogen atoms emit specific colors different from helium or iron. This creates a distinctive color fingerprint for each element. While this might be conceptualized as an element's color, from our everyday perspective, atoms are smaller than light wavelengths, making conventional color perception meaningless at the atomic scale. The force that holds the nucleus together. Overcoming Coulomb repulsion. One of the most profound questions in atomic physics concerns the nucleus itself. How do positively charged protons stay bound together despite their mutual electromagnetic repulsion? In nature, four fundamental forces govern all interactions: gravity, the weak force, electromagnetism, and the strong force. While gravity dominates at astronomical scales, the other three forces predominate at the quantum level. Electromagnetism, approximately 10 to the power of 37 times stronger than gravity, attracts electrons to protons in atoms. According to Coulomb's law, like charges repel each other, so multiple protons in atomic nuclei should violently repel one another. In a helium atom, for instance, two protons should experience enormous repulsion, causing them to fly apart instantly. Yet protons remain tightly bound in nuclei because of an even stronger force, the strong nuclear force. This force, approximately 100 times stronger than electromagnetism, operates only at the scale of atomic nuclei, about 10 to the power of -15 meters. While it functions differently from electromagnetism, it's powerful enough to overcome electromagnetic repulsion, keeping protons bound together. The strong nuclear force might be unfamiliar because it's rarely covered in educational curricula before the university level, yet it's fundamental to our existence. Quantum chromodynamics, the theory describing this force, explains how protons and neutrons remain tightly bound within atomic nuclei, resisting electromagnetic repulsion. Remarkably, the strong nuclear force constitutes approximately 99% of the mass of everyday objects, far more than the contribution from the Higgs field, which is often more prominently discussed in popular science. To understand the strong force more deeply, we must examine the composition of protons and neutrons. These subatomic particles contain even smaller entities called quarks, bound together by force-carrying particles called gluons. A proton consists of two up quarks and one down quark, while a neutron comprises two down quarks and one up quark. Gluons, which hold quarks together, possess a property called color charge, unrelated to visual colors, that comes in red, green, and blue, combining to form a neutral white charge. To achieve neutral charges, quarks must either combine all three colors or pair color with anticolor charges. the interaction between gluons and quarks binds them together with extraordinary strength. Unlike other forces, the strong force increases with distance, similar to a rubber band. When quarks move apart, the energy required to separate them eventually becomes sufficient to create a new quark-antiquark pair, a meson. This property ensures quarks never exist independently, they're always bound to at least one other quark. While the force binding quarks within individual protons and neutrons is strongest, a residual strong force also acts between nucleons, protons and neutrons. Though weaker than the force within nucleons, this residual force far exceeds the electromagnetic repulsion between positively charged protons. The strong nuclear force operates only at extremely short distances, approximately the diameter of a proton, and diminishes rapidly with increasing distance. This property limits the size of stable atomic nuclei, explaining why elements beyond a certain atomic number become increasingly unstable. The interplay between the strong nuclear force and electromagnetism determines which elements can exist naturally and which are unstable. Without this precise balance, the diverse elements necessary for complex chemistry, and ultimately for life, could not exist. The proton radius puzzle, redefining the fundamental. While you might assume our understanding of atomic properties like proton size has been definitively settled, a groundbreaking experiment in 2010 challenged existing knowledge by providing a significantly different measurement for the proton's radius. This discrepancy, called the proton radius puzzle, prompted scientists to re-examine fundamental assumptions about this basic building block of matter. Before exploring recent discoveries, it's important to clarify misconceptions about protons. Rather than being smooth, solid spheres, protons are more accurately described as clouds of quarks held together by gluons in a dynamic, constantly fluctuating arrangement. When physicists speak of the proton's size, they're referring to the boundary of its positive charge distribution. For decades, scientists used two main methods to determine this radius. The first involved directing electrons at hydrogen atoms, with a single proton nucleus and one electron, and observing how electrons scattered, revealing where the proton's positive charge begins to diminish. The second method measured energy transitions within hydrogen atoms. The electron in hydrogen doesn't simply orbit outside the proton, quantum mechanics shows it occasionally exists within the proton itself. This overlap between the negative electron and positive proton affects their electrical attraction, influencing the energy required for the electron to jump between energy levels. A larger proton theoretically allows more electron presence inside it, resulting in weaker binding. Using these methods, scientists had agreed on a proton radius of approximately 0.876 femtometers. A femtometer is 10 to the power of -15 meters, incredibly tiny. However, about a decade ago, a new approach dramatically changed this consensus. Instead of using electrons, scientists employed muons, particles similar to electrons but 207 times heavier. This increased mass causes muons to spend more time within the proton, making them millions of times more sensitive to proton size compared to electrons. In a landmark experiment using muonic hydrogen, where a muon replaces the electron, scientists measured a proton size approximately 4% smaller than the accepted value, about 0.833 femtometers. This seemingly small difference represented a major discrepancy that couldn't be reconciled with existing theories. The discovery prompted intense scrutiny of previous measurements and raised tantalizing questions about potential new physics or undiscovered particles. Was this evidence of unknown forces or particles affecting muons differently than electrons? Was our understanding of quantum electrodynamics incomplete? In September 2019, researchers at York University in Toronto conducted an experiment using standard electronic hydrogen with an advanced measuring technique called frequency offset separated oscillatory fields. By exciting the electron to higher energy states, they obtained results consistent with the muonic hydrogen experiment, indicating a proton radius of approximately 0.833 femtometers. This convergence of results from different methodologies suggested the discrepancy was likely due to measurement errors in earlier experiments rather than exotic new physics. Nevertheless, the proton radius puzzle illustrates how even our understanding of nature's most fundamental building blocks continues to evolve. Why matter feels solid, the illusion of emptiness. When contemplating the seemingly contradictory nature of atoms, where most space is actually empty, a macroscopic analogy proves illuminating. Imagine magnifying a table to 1 billion times its size, making its atoms comparable to melons. Despite this enormous magnification, the nucleus at each atom's center would remain invisibly small, as would the electrons in their probability clouds. This raises a profound question: if atoms are mostly empty space, why don't objects pass through each other? Why doesn't light simply penetrate the gaps between atomic components? To understand the solidity of matter and the sensation of touch, we must explore electrons' behavior within atoms. Rather than orbiting like predictable planets, electrons move more like a dynamic swarm, similar to birds or bees flying in coordinated patterns. While tracking individual electron movements is practically impossible due to their speed, their collective behavior forms distinctive patterns. These electron patterns aren't arbitrary but follow specific quantum mechanical rules, comparable to steps in a choreographed dance. Each electron strictly adheres to its pattern, and the Pauli exclusion principle ensures no two electrons within an atom perform the same dance step. They must have different quantum states. While electrons don't tire or lose energy in their stable orbits, they can transition between energy levels by absorbing or releasing energy. Moving to a higher energy pattern requires energy input, while dropping to a lower energy state releases energy, often as light. When light attempts to pass through material like a table, electrons in the atoms absorb energy from the light, transitioning to higher energy states. After a brief interval, these electrons release energy, potentially as light again. This continuous absorption and re-emission of photons, coupled with the changing electron energy states, creates what we perceive as reflection, opacity, and color. But if light doesn't penetrate far into solid objects, why do they feel solid to touch? When your finger approaches a table, the electrons in your finger atoms come near the electrons in the table atoms. As electrons from one atom approach another atom's nucleus, their established energy patterns are disrupted. An electron in a lower energy level around one nucleus cannot occupy the same energy level around another nucleus if that slot is already filled. The incoming electron must transition to an unoccupied, higher energy state, requiring energy. This energy comes from the force of your probing finger. Bringing all the atoms in your finger close to those in the table would require enormous energy, far more than your muscles can provide. The resistance you feel when pushing against the table results from this energy requirement, explaining why solid objects don't pass through each other despite being mostly empty space. Why atoms form molecules, the quest for stability. The visible universe consists of fewer than 100 naturally occurring elements, yet the diversity of chemical substances we observe in the cosmos and within living organisms is astounding. This remarkable variety exists because atoms rarely exist in isolation. Instead, they eagerly form chemical bonds with other atoms, creating molecules. This propensity for bonding generates an extensive array of chemical combinations and materials, contributing to the myriad phenomena observed in the universe and the intricate structures essential for life, energy sources, consciousness, and various large-scale processes. The universe avoids monotony because atoms form bonds, resulting in complex chemicals with properties fundamentally distinct from their individual constituent atoms. This fascinating behavior stems from energy considerations, a phenomenon deeply rooted in quantum mechanics. Essential chemicals that shape our everyday experiences predominantly exist as molecules rather than isolated atoms. Oxygen presents itself as O2, two oxygen atoms bound together, nitrogen as N2, and water as H2O, two hydrogen atoms and one oxygen atom. This prevalence of molecular forms reflects atoms' natural inclination to achieve their lowest energy state. Like a marble atop a hill that effortlessly rolls downward, systems throughout nature consistently strive to minimize their potential energy. This principle explains phenomena from river flow, water moving from higher to lower elevations, to atomic bonding. Hydrogen, the simplest atom with one proton and one electron, typically exists as H2, hydrogen gas. Quantum mechanics reveals why atoms form molecules as they seek lower energy states. When two hydrogen atoms approach each other, their negatively charged electrons initially repel. Simultaneously, each electron feels attraction toward the positively charged proton in the neighboring atom. At an optimal distance, a balance is established where electrons can be shared between atoms while minimizing repulsion. The total energy of this arrangement, two hydrogen atoms bound together, is lower than the energy of two separate hydrogen atoms. This energy reduction drives molecules to form naturally. Importantly, the attraction between atoms isn't solely determined by electron cloud repulsion. A multitude of quantum interactions shapes molecular formation. The total energy of a system, including kinetic energy, motion, and potential energy, position, ultimately governs atomic bonding. For a two-atom system like hydrogen, H2, calculating this energy requires considering electrons' kinetic energy, proton-proton repulsion, electron-electron repulsion, and electron-proton attraction. In quantum mechanics, these complex energy calculations are encapsulated in the Hamiltonian, representing the system's total energy. Solving the time-independent Schrödinger equation with this Hamiltonian reveals how energy changes as atoms approach each other. The solution typically shows a distinctive energy dip at an optimal separation distance. This dip represents the system's lowest energy state, where two hydrogen atoms form H2. In this configuration, atoms exist in a more contented state with lower energy than when separate. This electron-sharing arrangement, called a covalent bond, extends to countless combinations of atoms, creating the astonishing diversity of molecules that constitute our world. The stability of atoms relates directly to their electron arrangements in orbital shells surrounding the nucleus. Particularly stable configurations occur when atoms have specific electron counts, 2, 10, 18, 36, 54, or 86. These magic numbers correspond to the electron counts of noble gases, helium, neon, argon, etc., which are chemically inert and reluctant to bond with other elements. Atoms seek stability by achieving a complete valence, outermost, shell of electrons, either by sharing electrons through covalent bonds or transferring electrons through ionic bonds. The balance between the attractive forces driving electron sharing for a complete valence shell and the repulsive forces between electron clouds and nuclei determines molecular structure. The underlying reason for these magic numbers stems from quantum mechanics. The Schrödinger equation and the Pauli exclusion principle, which states that no two fermions, such as electrons, can occupy identical quantum states, create a system where specific numerical sequences result in the lowest potential energy. For multi-atom systems like water, H2O, comprehensive calculations become necessary to determine the exact bond angles and lengths that minimize potential energy. While these calculations grow increasingly complex with more atoms, the fundamental principle remains: molecules form because the resulting structures have lower energy states than isolated atoms. Neutron stars, cosmic atomic extremes. Neutron stars stand as some of the most extraordinary objects in the universe, colossal atomic nuclei stretching several kilometers in diameter with mind-boggling density and inherent violence. Their very existence raises a profound question: how can something so extreme possibly exist? A star's life represents a delicate balance between the relentless inward pull of gravity and the counteracting outward pressure generated by nuclear fusion reactions in its core. Deep within a star, hydrogen fuses into helium, releasing energy that maintains this equilibrium. As the hydrogen supply diminishes, stars with sufficient mass begin fusing helium into carbon. In massive stars, this fusion process continues in successive layers, creating increasingly heavier atomic nuclei. Carbon transforms into neon, which evolves into oxygen and silicon. This fusion chain culminates in the production of iron, an element that cannot undergo further fusion to release energy. Once a massive star develops an iron core, a critical turning point arrives. With fusion no longer generating energy to counteract gravity, the radiation pressure rapidly declines, disrupting the star's equilibrium. If the core exceeds approximately 1.4 solar masses, known as the Chandrasekhar limit, catastrophic collapse ensues. The outer layer of the core accelerates inward at velocities approaching 70,000 kilometers per second, collapsing toward the star's center. At this critical juncture, only the fundamental forces within atoms can potentially counteract the gravitational collapse. The weak nuclear force plays a crucial role during this collapse. In the hot, dense plasma, newly formed protons can transform into neutrons through electron capture. This process continues as temperatures and pressures rise dramatically, creating a neutron-rich environment. This neutron dominance stems from a seemingly arbitrary but crucial aspect of our universe's design, the masses of up and down quarks. Since down quarks are heavier than up quarks, and neutrons contain 2 down quarks, compared to protons with 2 up quarks, neutrons are slightly more massive than protons. Under normal conditions, this mass difference causes free neutrons to decay into protons. However, in the extreme environment of a collapsing stellar core, this process reverses. Protons and electrons combine to form neutrons, releasing neutrinos and creating what will become a neutron star. The neutron star represents an extreme state of matter where the entire stellar core transforms into a giant nucleus-like object composed almost entirely of neutrons. This transformation highlights the profound role that fundamental constants play in shaping our cosmic reality. Had the down quark been assigned a slightly lower mass during the universe's formation, neutrons might have been lighter than protons. This would have dramatically altered cosmic evolution, potentially creating a universe dominated by neutron-rich matter rather than protons. Such a universe would likely lack chemistry as we know it, with no possibility for conventional stars, planets, or life. The mass ratio between protons and neutrons, seemingly arbitrary yet precisely tuned, enables the proton-dominated universe we inhabit. This ratio allowed hydrogen to become the predominant element after the Big Bang, setting the stage for star formation, element creation, and ultimately, life itself. Additionally, our universe exhibits another crucial asymmetry, the prevalence of matter over antimatter. Had equal amounts of matter and antimatter formed and annihilated after the Big Bang, no matter would remain to form galaxies, stars, planets, or living beings. This matter-antimatter asymmetry represents another example of nature's fine-tuning that enables our existence. Neutron stars embody the extreme consequences of these fundamental physical properties. With densities comparable to atomic nuclei, around 10 to the power of 17 kg/m², a teaspoon of neutron star material would weigh approximately 1 billion tons on Earth. They represent the ultimate state of compressed matter before gravity would force collapse into a black hole. These extraordinary objects rotate rapidly, with some spinning hundreds of times per second, and possess magnetic fields trillions of times stronger than Earth's. When neutron stars form binary systems and eventually collide, they create ideal conditions for forming the heaviest elements in our universe, including gold and platinum, through a process called rapid neutron capture. This cosmic cycle, from hydrogen fusion in stars to neutron-star collisions that create heavy elements, completes the story of how atoms form and evolve throughout the universe's history, ultimately creating the diverse elements necessary for planets and life. Is our universe an atom in a larger cosmos? Could our entire universe, vast and complex as it seems to us, be merely a single atom within a much larger cosmic structure? This thought-provoking question bridges the immense and the infinitesimal, inviting us to consider profound connections between the quantum and cosmic scales. When we observe the universe, we witness how tiny subatomic particles combine to form progressively larger structures, from atoms to molecules, from celestial bodies to intricate living organisms. This naturally raises the question, could our universe itself be just a component of something even more grandiose? According to our current understanding of the universe's origin, it began as an infinitely dense singularity before expanding through the Big Bang. This implies that everything we currently comprehend was once unimaginably small. However, this initial singularity shouldn't be confused with an actual atom, as it contained the fundamental components necessary for atoms to eventually form. One intriguing concept in theoretical physics is the one-electron universe theory, which suggests that what we perceive as multiple electrons might actually be a single particle moving back and forth through time, creating the illusion of countless separate particles. While this specific idea lacks robust scientific support, it represents a thought-provoking starting point for considering deeper cosmic connections. A more scientifically grounded variation derives from multiverse theory, which proposes that every atom, electron, and property of matter in our universe could be equivalent to an atom in a larger cosmic scheme. This notion expands our conceptual framework, inviting contemplation of vast possibilities beyond our observable cosmos. The concept that our universe might be a tiny entity within a higher dimensional reality has intrigued science fiction writers for generations. In these speculative scenarios, our entire universe might appear as minuscule as subatomic particles seem to us, when viewed from the perspective of these hypothetical vast realms. Infinity plays a crucial role in these concepts. The multiverse theory suggests potentially infinitely larger universes might exist, making our cosmos, imposing as it seems to us, appear infinitesimally small from a more expansive perspective. String theory, a leading contender for a comprehensive theory of everything, offers mathematical frameworks that might support such hierarchical structures of reality. This theoretical approach envisions fundamental particles not as point-like objects but as tiny vibrating strings, with different vibration patterns creating different particles. In recent theoretical developments, researchers from Uppsala University in Sweden proposed a variation within string theory suggesting our universe might reside on the boundary of an eternally expanding bubble. In this model, everything familiar to us constitutes just a small segment of a much larger cosmic structure. Within this bubble, and potentially extending beyond its limits, additional dimensions could exist. The influx of dark energy, the mysterious force accelerating our universe's expansion, might originate from this broader bubble universe, offering a potential explanation for one of cosmology's greatest puzzles. If this unconventional portrayal of reality proved accurate, it would revolutionize our scientific understanding, positioning humans as infinitesimally small components within an incomprehensibly vast and complex structure. However, it's crucial to recognize that while intellectually stimulating, these concepts remain speculative, awaiting further theoretical development and experimental evidence. Nevertheless, even if our perspective proves limited and our understanding imperfect, the potential cosmic insignificance from an alternate viewpoint doesn't diminish the intrinsic value of our existence or the wonder of the universe we can observe and study. The very capacity to contemplate such profound questions demonstrates the remarkable nature of consciousness itself, perhaps the universe's most extraordinary emergence. The journey of atoms after death, cosmic recycling. Throughout human history, over 100 billion people have lived and died. Considering the law of conservation of matter, which states that matter cannot be created or destroyed, only transformed, an intriguing question arises: what happens to all these atoms after death? Let's explore the fascinating possibility that the atoms from your departed loved ones haven't vanished but have become an integral part of you, the world around you, and are presently embarking on a remarkable journey across the universe. The human body consists of approximately 60% water, 20% fat, 15% proteins, 2% carbohydrates, 2% minerals and salts, and 1% other elements including oxygen, gases, and vitamins. When someone dies, these components undergo transformative processes. Water, which forms the majority of our bodies, either evaporates or seeps into the ground. The speed of this process depends on environmental conditions such as temperature and humidity. Even in liquid form, this water eventually enters Earth's water cycle, transitioning between liquid, vapor, and precipitation. Some of this water returns as rain, potentially becoming part of your drinking water. Your body uses this water for numerous functions, integrating it into cells, regulating temperature, and supporting various physiological processes. Some rainwater is absorbed by plants for photosynthesis, combining with carbon dioxide and sunlight to produce carbohydrates and oxygen. The oxygen released during photosynthesis becomes part of the air you breathe, while plants convert the water and carbon dioxide into carbohydrates that you consume in fruits and vegetables. This demonstrates how atoms from deceased individuals continue circulating through the ecosystem, connecting all living beings in a continuous cycle. The soft tissues in a human body, carbohydrates, fats, and proteins, undergo metabolism after death, facilitated by approximately 100 trillion bacteria that reside primarily in the gut. During life, the immune system keeps these bacteria in check, but after death, they begin consuming the body's tissues. As bacteria metabolize these tissues, they convert them into energy for their own survival and reproduction. This process resembles a gradual burn, transforming molecules into water and carbon dioxide, the same compounds produced during combustion. Additionally, proteins break down into gases like nitrogen oxides and ammonia. Interestingly, some of these gases, particularly nitrogen oxides, are potent greenhouse gases, approximately 300 times more effective than carbon dioxide at trapping heat in the atmosphere. This highlights how human remains continue participating in environmental processes even after death. As oxygen becomes scarce during decomposition, anaerobic bacteria take over, producing byproducts like methane, hydrogen sulfide, and ammonia, creating the characteristic odors associated with decay. These substances eventually escape the body and disperse into the atmosphere. Furthermore, decomposition releases various elements into the soil, approximately 32 g of nitrogen, 10 g of phosphorus, 4 g of potassium, and 1 g of magnesium per kilogram of dry body mass. These components act as natural fertilizers for surrounding plants, enriching the local ecosystem. Cremation offers an alternative perspective on atomic transformation. The intense heat converts most atoms in the body, hydrogen, carbon, nitrogen, oxygen, and sulfur, into gases released into the atmosphere. The remaining ashes, weighing approximately the same as a person's birth weight, consist primarily of phosphate and calcium from bone structure. These ashes typically enter the soil, becoming incorporated into plants, which may later nourish animals and humans. Through this pathway, small amounts of atoms from cremated individuals could eventually reside in the bodies of their descendants, perhaps in a morning cereal or hamburger consumed by future generations. Radioactive elements in the body follow a different path. Through radioactive decay, they transform into other elements before entering the biosphere. For example, radioactive potassium may become calcium, while thorium and uranium eventually transform into lead. This decay process also generates helium atoms, some of which escape Earth's gravity into space, while others remain captured by massive celestial bodies like the Sun and Jupiter. A portion of atoms from decomposed bodies embark on extraordinary journeys beyond our solar system. These atoms drift among the stars, venturing to the cosmos's farthest reaches, existing in perpetual motion that transcends time itself. The eternity question: do atoms last forever? While life on Earth appears relatively constant and predictable, marked by the rhythmic ebb and flow of tides, the daily cycle of the sun, and the unchanging progression of seasons, the larger cosmic panorama reveals a dynamic tapestry of constant change. Each day throughout the universe, millions of stars are born while others die. Even our own sun, seemingly eternal from our perspective, faces an inevitable end billions of years in the future. As it transitions into a red giant, Earth will experience rising temperatures, ultimately becoming uninhabitable. A few billion years later, the sun will exhaust its nuclear fusion fuel, initiating its final decline. In this cosmic perspective, nothing in our universe truly endures eternally, or does it? What about atoms, the fundamental building blocks of all matter? When we contemplate our individual mortality, it's important to recognize that our bodies, composed of these atoms, don't simply vanish into nothingness. Instead, they transform, embarking on intricate journeys that extend beyond our limited lifespans. Our bodies break down into their fundamental components, becoming reintegrated into the ecosystem in various forms. How long can atoms themselves endure? Is there a point at which they cease to exist? Answering these questions requires exploring atomic structure more deeply. Atoms consist of protons and neutrons in a central nucleus, surrounded by electron clouds. An atom's stability hinges on the balance between electrons and protons. The atomic number, which determines an element's identity, equals the number of protons. Helium has an atomic number of 2 because it contains 2 protons. While the number of neutrons typically remains constant within a specific isotope, variations occur. When an atom lacks the correct neutron count, it may shed a neutron through decay processes. This imbalance renders the atom unstable, prompting it to emit subatomic particles as it seeks equilibrium. Heavier atoms often undergo spontaneous breakdown into smaller components through radioactive decay. This process occurs randomly at the individual atom level, making it impossible to predict exactly when a specific atom will decay. However, statistical analysis allows scientists to estimate the average time required for half the atoms in a sample to undergo decay, a measurement known as half-life. Since atoms possess finite numbers of protons and neutrons, they generally emit particles until reaching a configuration where their half-life becomes so extensive that they're essentially stable. Bismuth-209, for example, was long considered stable until scientists discovered it undergoes alpha decay with an extraordinary half-life exceeding 10 to the power of 19 years, more than 1 billion times longer than the current estimated age of the universe. This raises an intriguing question about the potential for eternal life at the subatomic level. Theoretical models like the Georgi-Glashow model propose that protons might eventually decay into positrons and neutral pions, which subsequently transform into gamma-ray photons. This model suggests a proton half-life of approximately 1.29 times 10 to the power of 34 years, an almost incomprehensibly long duration. However, it's important to note that no experimental evidence currently confirms proton decay. Despite this absence of proof, ongoing research at leading laboratories worldwide continues exploring this possibility. Through a combination of theoretical advancement and experimental investigation, scientists hope to eventually determine whether protons, and by extension, atoms, can truly last forever. Conclusion: the cosmic perspective. From stars being born in distant nebulae to tiny particles silently transforming, the universe performs a beautiful dance of creation and metamorphosis. In this grand cosmic ballet, atoms serve as the connecting thread between past, present, and future, carrying within them the history of ancient times, distant stars, and countless galaxies. At the heart of this journey lies a profound truth: the atoms in your body have existed since nearly the beginning of time. They've witnessed the formation of the first stars, survived supernova explosions, drifted through interstellar clouds, and coalesced into our solar system. These atoms have been part of countless entities before becoming you, and will continue their journey long after your conscious experience ends. This atomic perspective reveals a deeper connection with everything around us. The carbon in your cells was forged in stellar furnaces billions of years ago. The iron in your blood came from exploding stars. The water that constitutes much of your body has cycled through oceans, clouds, and countless organisms throughout Earth's history. Through atoms, we discover that the boundaries between you and not you blur at the fundamental level. The atoms composing your body today will, over time, become part of other people, animals, plants, the soil, the air, and eventually, perhaps even distant stars. This continuous recycling connects us physically to everything that has existed and will exist. What makes this even more remarkable is that atoms themselves don't know what they're part of. The same carbon atom could exist in a diamond, a plant, or your brain, experiencing radically different realities based on its arrangement and interactions. Consciousness itself emerges from particular configurations of these mindless particles, a mystery that continues to challenge our understanding. As we journey through the vast cosmos in the quantum realm, we discover that everything, from the largest galaxies to the smallest particles, is connected in ways that inspire both scientific inquiry and philosophical wonder. Our brief moment of consciousness offers a unique opportunity to contemplate the atoms that compose us, to understand our place in the cosmic story and appreciate the extraordinary journey that brought these particles into this particular arrangement we call human. In the dance of atomic particles, we find echoes of our own ephemeral nature and the profound interconnectedness of all existence. Like atoms, we are both transient in our current form and eternal in our essence, participating in a cosmic cycle that began long before our birth and will continue long after our departure. Thank you for joining this exploration of atomic origins, the remarkable journey from nothing to everything that created us all and connects us to the entire cosmos.